Okay. So I've had several homework submissions coming in. I don't think everybody vote. Um, so um, hopefully, the rest of you can get your assignments in by sometime tonight, or at least by tomorrow morning, and then presumably toward the end of the week or on the weekend, I'll just ruin my weekend grading these things. Although it won't be as ruined if everybody did well. So it always makes things go faster. It's when grading, it's answers that are clearly right or clearly wrong are easy to handle. It's the answers that are weird, where you're not really sure if it's right or wrong, and you have to check if it is equivalent to what you were looking for, and that's when this gets a bit onerous. So, okay. Now, so this is the last day being spent on LU decomposition. And so I just realized only a few minutes ago, so I took a while getting set up. Because I keep updating the same notes for this section. So they're dated January 29th when I started covering it. And so the notes were updated on Monday's class, and I forgot to put that on the site until just now. And of course, today I'm going to add more to them, and I'll be sure to get that up on the site a lot faster. So these 3 days spent on LU, the link to the notes is going to be to the same file. It's just going to keep getting updated as I go through a section. And that'll happen in a lot of cases where there's more than 1 day spent on a section. Okay. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Where's Samson? Oh, okay. I knew Carly wasn't going to be here, so yeah. Trying to make sure everyone's accounted for. Okay. Now, so where I left off last time, pivoting strategies. So the idea is we want to interchange rows in such a way that, or rearrange the system of equations in such a way that the multipliers that come up during Gaussian elimination are smaller. So that will naturally address any potential division by zero. Also, it'll help limit the propagation of round-off error that comes from floating point arithmetic. So partial pivoting was one such scheme. We're working on a particular column, and we just look within that column and swap so that the largest element possible is on the diagonal, since the multipliers are given by this ratio. So if we make a diagonal element larger, that'll make the whole multiplier smaller. Now, we can take this one step further, and that leads to another popular pivoting scheme called complete pivoting. So the idea is, before eliminating subdiagonal entries in a particular column, we examine rows and columns, j, j plus 1, and so forth, all the way to the end, to find the largest elements. Okay, so we're covering a lot more territory. So once we find the largest element in that whole submatrix, starting from rows and columns j plus j all the way down to the bottom, or to the right, and then swap. Okay, so suppose that entry is A, PQ. So we find it in row P in column Q, and because of where we're looking for it, those indices have to be j or larger. So we swap rows j. Stop that. Love how it decides on its own that when I type a $, I actually want a $. Like, no, I want math mode. I'm never going to talk about money in numerical analysis. Okay, so whatever row we found at largest entry, and we'll swap those rows. And columns, J and Q. So that entry, the largest one we found, is put on the diagonal. Okay. So what happens is, so A is replaced by, okay. By a product of matrices, P1A, P2. Now, I need to describe what these P1 and P2 are. P2 are what are called permutation matrices. So I'm just going to make one up as an example. So I'm going to start by filling in the identity matrix. Okay. Now, just like other elementary row matrices, elementary row matrix is what you get when you take the operation you want to perform and apply it to the identity matrix. So in this case, we're swapping rows. So I'm going to swap rows 2 and 4. Something went wrong here. Okay. So I'll move row 4 into the second position. Okay. So swaps rows 2 and 4 if multiplied on the left. If you multiply by a matrix like this on the right, it swaps columns. Okay, now, so what happens when you replace A by this? Because your P1 is meant to swap rows, P2 is meant to swap columns. The system that you started with well, I need to multiply on the left by P1. So I need to do that on both sides, certainly. Okay. Now, but the thing is, I also need to multiply on the right of A by P2. So I'm going to fill in P2 here, but I can't just shove a P2 in there and leave it at that, because A is supposed to be multiplying X. So if I'm going to put a P2 in there, what else do I need to put in there to like compensate so that the overall expression is not changing? P2 inverse. Okay. Whoops, there should be... Okay. P2 inverse. Now, so then X is still the solution of the original system. So But really what I'm doing is solving this system. I'll call it tilde A. And then tilde X equals tilde B. Where tilde A is just the A with the permutations applied. And then B, or tilde B, is the original B with only the row operation, row interchange is applied. And then tilde X equals P2 inverse X. Okay, so this system, there's no more interchanges to apply. They've been applied here. So with this matrix A tilde, we would actually carry out the LU decomposition, and because the pivoting has been applied, that LU decomposition would exist. So then we can go ahead and solve. So we can carry out the following: tilde A equals LU, and then forward substitution. L y is equal to B tilde, and then U X tilde is equal to Y, using so back substitution. Okay. Okay. Now, once that's done, well, it's X that we want. So I need to take this equation and solve it for X. Well, X is equal to P2 tilde X. Okay. So that is a system, solution of the original system. So when you're swapping rows, all you're doing is rearranging the order of equations. But if you're swapping columns, then you're changing the order of the unknowns. So if you're going to do that, you have to unscramble those unknowns at the end of a process. Now, the nice thing is we didn't actually have to know P2 inverse. It's really just P2. So applying these, so all I did was here, I multiplied both sides by P2. So now we see how to get X. Okay. So questions about how we would solve a system in a case where we are swapping rows and columns. Okay. Now, okay. So complete pivoting as opposed to partial pivoting, what are pros and cons? So the pro, I'll go to a new page. Okay. All right. Smaller multipliers than partial pivoting. Because whatever largest entry you find in various rows and columns to swap, to move into the JJ position, it's certainly going to be larger than what you would find if only looking in column J. So that'll lead to smaller multipliers. So the benefits of that, so less propagation of rounding error. Excuse me. Also, Gaussian elimination is proven to be backward stable. Now, this is a backward error analysis. Backward error is something that was covered extensively in 460. Although I don't know if Dr. Chen covered that when he taught it, but I do. It's in Chapter 2, or actually, more specifically, Section 2.1. So what I mean when I say the Gaussian elimination is backward stable, that the computed output of Gaussian elimination, in other words, the LU factors, is the exact LU decomposition of a nearby problem. So the nearby matrix. So because of rounding error, the L and U that you get, they're not the exact LU decomposition of the A that you gave it. But you can say that at least they are the exact LU factors of a matrix that is close to A. So in other words, the backward error can be reasonably bounded. If we recall from this error analysis that forward error, so in this case, error in the output, is backward error, in this case, error in A, times the condition number of A. Now, in 560, when I define condition number, it's for a very general problem. So the indication of how much the solution may change if the input is changed. Later in this chapter, section 3.4, I'll get to condition number specifically for AX equals B. So by using our knowledge of this problem, we can get something a lot more concrete. So if a backward error is kept small, then hopefully the forward error is also kept small, at least if a problem is well conditioned, meaning the condition number is not too large. Okay. Now, whereas this kind of theory is it's not proven to be backward stable in the case of only partial pivoting. Now, to help you appreciate this, I'm going to go into the history a little bit when it comes to Gaussian elimination. Because back when electronic computers were first invented, so we're talking back in the 50s, so then Gaussian elimination was used on such computers to solve systems. Gaussian elimination had already been in existence for such a long time, but only when electronic computers were around, they came on the scene, then round-off error needed to be considered. So then people began to wonder, once round-off error is in the picture, can the solution output by Gaussian elimination and forward and back substitution, can it be trusted? It wasn't really clear back then, and there were those who believed that Gaussian elimination with rounding error was simply unstable. And can you imagine if that turned out to really be true? Well, what will we do? So Jim Wilkinson, one of the great figures of numerical linear algebra, he did a very careful round-off error analysis that studied the propagation of round-off error throughout the entire algorithm. And what he showed that, yes, Gaussian elimination is stable, although you do need pivoting You need to keep the size of those multipliers in check to ensure that. So if Gaussian elimination had turned out to be unstable, we would not be totally dead in the water as far as solving systems, because there are other methods. There are iterative methods, for instance. And I will be spending a little time on those, like a little bit of Chapter 5. But all these methods have difficulty if the problem is ill-conditioned, that the solution is very sensitive to changes in A or B. Okay, so because you could have an algorithm that is really accurate, really efficient, looks great on paper, and maybe the exact arithmetic would be a very effective solution technique. But if it can't handle round-off error, if it appears to be too sensitive to it, it's not going to be used. So something to be very mindful of. That's like the dark side of numerical analysis. That if you're not careful, seemingly good algorithms could turn out to not be so good after all. Okay. Now, on the con side of complete pivoting, it's a lot more expensive, order n cubed comparisons, because you're searching a whole submatrix for which row and column to swap with. Now, each time you're going to perform one row swap and one column swap. So the total number of swaps is no big deal. It's only twice as many as in partial pivoting, because in partial pivoting, when you come to each column, you make one row swap. In complete pivoting, you make one row swap and one column swap. But to find out which row and column to swap, it's order of magnitude more entries to look at. So this is a problem because Gaussian elimination as a whole requires 2/3 n cubed arithmetic operations. So if the comparison part is on the same order of magnitude of expense as the arithmetic part, and for a large matrix, that adds significant overhead, whereas partial pivoting, the overhead is fairly negligible. And while complete pivoting is more reliable, generally partial pivoting works well enough to get accurate solutions to AX equals B. I mean, there are certain pathological cases, and one of these actually comes up in the homework, where it turns out that partial pivoting still gives you a bad decomposition, and from a round-off error standpoint. But for the general case, partial pivoting is good enough. Okay. And for not so much overhead. So still, partial pivoting is what's most commonly used. But if rounding error or conditioning stuff you're really worried about, then you might want to use complete pivoting. Okay. So that's all I'm going to say about complete pivoting. So what about the algorithm for AX equals B? Okay. Now, so what we do is A equals LU, Gaussian elimination, and then L, Y equals B. And then UX equals Y. Back substitution. Okay, so the question is, how does this change when rows are interchanged. What does that do to this whole process? Now, to get a definitive answer here, how Gaussian elimination without pivoting worked before is you started with A, and you wanted to get to this upper triangular U. So what you would do is multiply on the left by these matrices M1, M2. Each one of these matrices, M matrices, would work on eliminating entries in in that column. So M1 works in the first column, M2 works in the second column, and so forth. Mn-1 works on the one and only entry to eliminate in column n-1, and then that would be it. You'd have upper triangular form. But now, if pivoting, partial pivoting only, so we're only going to swap rows, not columns, what happens is before we work on a column, we may do a row interchange. So, in other words, we're going to multiply by permutation matrix P1. That will swap row 1 with some other row. Or maybe nothing. If there's no swap, then this P1 would just be identity. But we don't know, so we'll assume that there's some swap happening. Then, the largest entry is in the first row, first column. We eliminate those entries. Then we move to the second column. Before we eliminate entries there, we multiply by another permutation matrix P2, then P3, and then we keep going all the way down to Pn-1. So swap, eliminate, and so forth from columns 1 all the way to n-1. Now, but we have this problem. The way L was defined before is equal to the inverses of all these m's. Okay. Now, an L is meant to be unit lower triangular, just as all these m's are unit lower triangular. But if I were to move all these matrices to the other side by multiplying by inverses on the left, I would not have a product like this. I'd have this interlacing with all these permutation matrices. And the result is not going to be unit lower triangular. So I still want the same kind of factorization. I would like to break things down into a product of a unit lower triangular matrix and an upper triangular matrix. So how can I do that? With some hocus pocus of matrix algebra. So I'm going to go back up to here and mess with things a little bit, or actually a lot. So what I'm going to do here is I'm going to, I would like to have all of the m's to the left, all of the p's to the right. Now I can't just move these around, because matrix multiplication is not commutative. But I want to get some sort of expression where I have unit lower triangular matrices for eliminating on the left, permutation matrices for swapping rows to the right. Now P1 is already in the right place, but I'd like to move P2 over. So here's what I'm going to do. I'll put P2 here, but just like before, I have to compensate. Okay. So now I have P2 inverse. Now, I'm going to group these together. So I take M1, which is a unit lower triangular matrix. Now, by multiplying by P2 on the left, I am swapping rows, which will destroy unit lower triangular structure. But then I will swap columns by multiplying on the right. And that will actually restore unit lower triangular structure. Now, to get an idea of why this would happen, okay, I want to be able to show you in Matlab. Now, before I go further, okay, a permutation matrix is an example of what's called orthogonal matrix. When you have an orthogonal matrix, P transpose P is the identity. Or, put another way, P inverse is equal to P transpose. So that's very convenient. So it's very easy to get the inverse of a permutation matrix, which happens to be applying the inverse permutation, because permutations in general have an inverse. And you get it just by applying, by taking the transpose. So now, so a key observation to make here is that tilde M1, which is defined to be P2 M1 P2 transpose, so instead of inverse, is unit lower triangular. Now, to try to show you a proof of this would be quite tedious, but what I'll do is I'll do a Matlab demonstration. Because it might be hard to believe it's just by seeing it written out here. Okay, so I'm going to make up a matrix M, star of identity matrix, and then I'm going to put in rows 2 through 4, first column, some multipliers. So this is what an actual M1 would look like. Okay, so something like this. Okay, now I'm going to also make up a permutation matrix by first making the identity. Now, what would P2 do? P2 has to swap row 2 with some row below it. So, to swap, shoot, I should have done a diary. And actually, I think it's some other diaries. Yeah, I have a diary for Monday I need to put up. Hold on. Okay. All right. I'm just going to repeat these commands. Okay. Okay, so now I have an identity matrix, but I wanted to swap row 2 with something below it. So I'm going to say rows 2 and 4 of P, I will set them equal to rows 4 and 2 of P, and that will accomplish the swap. So there's P, and we see that rows 2 and 4 are interchanged. Okay, now I'm going to then swap so I apply this permutation matrix to M on the left. Now M right here is unit lower triangular. I swap rows. Well, it's not unit lower triangular anymore. Okay. But notice this column here, not touched. It's column 1 because that was M1. M1 works on column 1. So whatever interchanges take place here are never touching the multipliers because what happens is M1 is affected by P2. So then what I do is multiply by P transpose now on the right, which will swap these columns. Now the swapping items 2 and 4 is undone by swapping items 2 and 4 again. So, and now unit lower triangularity is restored. So what's very important here is that it's swapping of columns of identity. And at least this portion of identity that gets affected by the permutation. So that's why we can be certain that by rearranging these rows of identity and then rearranging those same columns of identity, we get back to that portion of identity for that portion of a matrix. And that's why we can be certain that applying this permutation matrix on the left and then the right will keep this unit lower triangular structure. So now what I can do, if I update this equation, so this will be M1 tilde now. Okay. So now progress is being made that I have these two permutation matrices out of the way. But now I need to move P3 over here also. So now what I'll do is I'll put a P3 here. And therefore, I need to put P3 inverse, or P3 transpose, also. So now I have this matrix to look at. P3 applied to the product M1, M2. But the thing is, once again, M1 works on column 1. M2 works on column 2. P3 will swap rows or columns 3 to n. So this matrix, again, once all permutations are applied to columns and rows on the left, columns on the right, will turn out to be still unit lower triangular. So I can keep doing this, and eventually all permutation matrices will be on the right, and then these m's, which are modified, turn out to be on the left. But there's one thing, I just realized I made a slightly erroneous statement. I said this column was untouched, and that's not exactly true. If I look at M1, the original M, right here, and then the modified, the overall structure of a first column did not change. But what changed about that column? Yes. So rows 2 and 4 of this column were still swapped. Okay. And that's going to be very important because of the following. So effectively, what we have is the following, that Okay, so P1, P2, etc., all the way down to P n minus 1. So all the row swaps. So in other words, you can apply all the row swaps to A, and then the elimination. I need to put tildes in front of these. Oh, I need to put dot in here also. Okay. Okay. So this is what happens. Where so if a matrix that works in column J is equal to okay. All right, so P2, P3. Okay, so this has a P2. Okay. So each J effectively has all later permutations applied to it. That's to be the permutation matrices themselves on the left, and then their transposes on the right. That is still unit lower triangular. Okay. So whatever row operations are performed when you get to that column, then whatever row interchanges happen after that still have to be applied. So then we have the following: PA equals LU. So where P carries out all row interchanges, so it's the cumulative effect of all of those row interchanges. And L still contains multipliers. But there's one very important point. Because in Gaussian elimination, I mentioned that the most efficient thing to do is when you get a multiplier, you just store it in the lower triangular part of a matrix. So here's how you implement the algorithm. Okay. For efficient storage and, of course, correctness. So when you compute the multiplier that you're about to use for row operation, store it in that, so whatever entry you're eliminating, ij entry, that's where you put it. And keep in mind, I is greater than j for any entry we're eliminating, so it's always going to be in the lower triangle. It's not going to mess with your final result of Gaussian elimination, your row echelon form. Then, when interchanging rows at any point during the algorithm, apply the interchange to the entire rows. So row J and P. So P is a row that you're swapping with row J to get multipliers less than or equal to 1 in magnitude. So, because you might think, well, when you're interchanging rows, you only have to interchange a portion of a row that you're working on for elimination, like within U. Well, you do need to apply it to that. But if you apply it to the stored multipliers also, that has the effect of carrying out this for you. So it's a very easy way to ensure that multipliers are in the right place within L. So this ensures the correct L in the factorization you're going to get, PA equals LU. So while this is pretty nasty matrix algebra to see what's going on here, to try to rewrite this as terms of permutation matrices followed by elimination matrices. Oh, that reminds me, up here, I forgot the tilde. Okay. But in terms of implementing Gaussian elimination with pivoting to get to a proper L, it's very, so from a coding point of view, it's quite easy to do. So swap the entire row, not just a portion of it. Okay. So now, if I go back to the algorithm for solving AX equals B, okay, so now it's PA equals LU. So that's Gaussian elimination with pivoting. So as you perform row interchanges, what you can do is you can start with a vector of indices 1 to n. And then as you swap rows, you swap those indices. I'll say more about that in a moment. But Gaussian elimination with pivoting will produce this result. So this L and U, and then you'll have some indication of what rows were swapped along the way. Then, for forward substitution, it's not Ly equals B, it's Ly equal PB. So whatever row interchanges you apply to A, of course you have to apply them to B. So, because you had AX equals B, well, that means PAX is equal to PB. And then back substitution, that part doesn't change at all. So this is the algorithm for solving AX equals B when you're doing row swaps. Okay. Do not store P explicitly. Can anyone think of why it's inefficient to store the matrix P as a matrix such as this? What's impractical about that? What?
It would change A steps in the middle.
Well, yeah, you're changing A as you go. And the thing is, when you're doing that, you could form this P explicitly. Like, you can start with an identity matrix, and when you're swapping rows 2 and 5 of A, you can also swap rows 2 and 5 of this identity matrix, again, as you go, and end up with P. That you could then multiply with B to get this. But the problem is, a permutation matrix is a matrix consisting of only 1s and 0s. And you also know how many 1s there are. If an n by n matrix, there'll be n entries that are equal to 1. And you're storing all these zeros. So it'd be nice to have a more compact representation of P than a full n by n matrix where almost all the entries are 0. Now, a different way of doing this, what I recommend is the following. Start with a vector of indices 1 to n. when swapping rows of A, swap indices in this vector. So what you end up with is, at the end of the algorithm, the order of the indices that you have corresponds to the final ordering of a row is in A. So if 1 is in the fifth position, that means that that's where row 1 in A ended up after whatever swaps. Okay. Then use these indices to rearrange B. So in Matlab, that's very easy to do. So P is not a matrix, but just a vector of scrambled indices from 1 to n. If you do this, B of P, it will select the elements of B, the original B, but it'll select those entries in that order. So that alone is enough to do the rearrangement. So no matrix vector multiplication involved, like you see here. Again, that would be very wasteful. Okay. So that's the whole algorithm. How it's changed when you include partial pivoting or any other scheme that swaps just rows. Okay. So questions about what happened here? One of the problems in homework 2 involves implementing Gauss elimination with partial pivoting. So some of the things I mentioned here about how you represent P, and also this will play a role in that problem. Oh, shoot. Yeah. I have to remember to post hints for every homework from 2 on. Okay, well, at least that one's not due for a week. I'll get those hints up. Feel free to remind me. I would put them here on the assignments page. I just need to look at them from last time. Okay. Now, the last thing to cover, I mentioned before determinants, how it's pretty easy to get them once you have the LU decomposition. And that is also true in the case of Gauss elimination with pivoting, but there's a little more involved. So the determinant of A, what I could do is if PA equals LU, I can multiply both sides by P transpose. So now I have that. But remember, determinant of a product is the product of determinants. And determinant of a matrix is the same as determinant of its transpose. The determinant of L is 1 because it's unit lower triangular. And we know that the determinant of U is just the product of the diagonal entries. So what about the determinant of P? What would that be? Since P is a real orthogonal matrix, so P transpose P is equal to identity. So if we take a look at that, take a determinant both sides. So determinant of identity, which of course is 1. So that's the determinant of P transpose P, using the same properties as before. I have determinant of P times determinant of P. So we know about the determinant of P, since it's determinant of P squared is 1, the determinant of P is plus or minus 1. So how do we know whether it's plus or minus 1? The fact that interchanging rows of a matrix, or columns, doesn't matter, negates the determinant. So now we have the following. So every time a row swap is made, it changes the sign. So it's minus 1 to the S times the product of all the diagonal entries of U, where S is the number so how many row interchanges were performed. Now, keep in mind, when you do these row swaps, sometimes you decide not to swap a row, that the correct element is already in that position. So that one would not count. So S is not going to be N. It's going to be less than or equal to N. So as long as you take into account the number of row interchanges, then the determinant will have the correct sign. So even with pivoting involved, it's still quite easy to get. Whether if it's useful information is another matter. Okay. So now I've finally reached the end of a section. That was a long one. Okay. Now, well, we have time for questions about anything such as, well, you guys are either wrapping up homework 1 or some of you might be getting an early start on homework 2. Doesn't matter to me. Are there any questions about anything there? I know I still have quizzes to grade. Well, actually, now I'm going to have a lot of stuff to grade. I'll catch up soon, I promise. Yes?
What is the output argument on 3.2.11 supposed to be?
3.2.11.
I mean, what is the alpha supposed to be? Is it the whole LU?
Oh, okay. So it'll contain L and U. So the upper triangle will contain U, the row echelon form. The multipliers will be stored in the lower triangle. So it's the interesting part of L. And because with L, you don't need the diagonal to store because it's all one. So in other words, as you're going through Gaussian elimination, as you compute a multiplier, you put it in that spot. And actually, I remember last time I gave this problem, 2 years ago. Actually, I think also when I gave this in 610, 1 year ago, that a lot of people didn't follow this for whatever reason. So what I want is just one matrix that has multipliers below the diagonal, row echelon form above.
The same dimensions as A?
Yeah, same size as A. Because really, you're literally using A. You're overriding A with the important parts of the L and U factors. Other homework questions? Y'all just want to leave early. Well, I can't fault you for that now, can I? It's been a long day since I've this class at the end of the day, and then my first class at 9:30, and I have to be here at 8:30 just to find a place to park. Yes.
I have a question about the one for the first homework.
Okay.
About the Gaussian elimination one.
Okay.
I think it's the last one. Is that? Yeah.
Okay.
So I have pretty much there. All we're supposed to do is put in the algorithm, right, and assign it to a random matrix.
Yeah.
Okay.
So you're talking about 3.1. Wait. Oh, I didn't sign this one.
No, it's 3.1.7.
Oh, okay. Yeah.
Yeah. So we're just supposed to put in the algorithm and then make it work.
Yeah. Now, a thing to keep in mind, I should have mentioned this earlier because it's something I've gotten some questions about. The A that comes out is not going to be upper triangular. And the reason why is because of this. K starting at J plus 1 and going to N. So the upper triangle of the returned A will have the correct row echelon form. The lower triangle will actually be the original the elements of A that were there before. They're not touched. If you change this loop, K going from J to N, then A will come out as upper triangular. So you could try that as a way to check. And actually, another thing you could do if you want to check is if you actually do what's actually required to be done in the problem that Jake was asking about. Go ahead and store this not as its own thing, but actually store it as Aij set equal to this. So you're overriding the lower triangle with the multipliers. Then what you could do is you go to your output and take the upper triangular part, that's U, the lower triangle below the diagonal with ones, that's L. Then L times U should equal A. So it's kind of a pain to check that, but but that's one way in which you could. MATLAB does have an LU function for computing LU decomposition. The problem is it's going to pivot. So even though this algorithm just doesn't bother with it, and MATLAB's LU, I'm not really aware of a way you can tell it not to pivot, because if you could, then that would provide an easy way to check. Okay. It's not as conclusive, but if you go ahead and use backslash to solve AX equals B, you do A backslash B with the original A and B, and do it again with a modified, those should match. So if they do, then chances are what you have is right. Okay. Any other homework questions, since we still have 8 minutes?
Just to comment on that.
Yeah.
The way I checked mine was after doing this, I just used the back sub function root.
Oh yeah, you can use a back sub. Oh, you know what? I just realized. I goofed earlier. You could use backslash on this to get the solution. You can't use backslash on this directly. Back sub would work. The reason why is A still has junk in the lower triangle. That would throw off backslash. If you took the upper triangular part of this, it's like try U of A, and do backslash on that, that would compute the solution. But the easier thing to do is use your back sub function. So it's a way to check both at once. Because if you look at the back substitution algorithm, where is that? Here. It looks at Uij, where j is greater than or equal to I. In other words, it only looks at the upper triangle. So this algorithm assumes the matrix is upper triangular, but if you just give it whatever matrix that has junk in the lower triangle, it'll ignore it. So that's why using back sub would be just fine. Okay. Any other questions? Yeah.
Quick general question.
Yeah.
Not last program where the output argument is a vector.
Oh, wait.
Or the AB, just the Gaussian.
Oh, okay. Yeah.
I can never get B to output, and I've never really bothered to figure out why.
Wait, you can't get B as output?
Well, when I just solve for them, it only outputs A, not B.
Oh, now, does that happen when you're actually typing just this?
No, it's happened with every function that's been.
No, what I mean is, okay, by default, if you call, if what I've highlighted there is what you type at the prompt, it'll only show the first output. Now, if you're doing this, like the whole line, it should show you both A and B. Okay, but yeah, it's a strange behavior of Matlab that it only shows the first output when there's no assignment. All right. Anything more?
So we got 3 weeks to our first test, right?
Yes, 3 weeks from today. So it means I need to get a practice test going. Actually, need to do that for both my classes. Oh, that's a ruined weekend. Okay. Alrighty, and then okay, really, there's only going to be 2 more sections on that. So certain classes matrices, symmetric, positive, definite, and banded, and then about the condition number, and
So how is the first step? Do we have to submit a code in it too? Like in the Michael one, we didn't have to write the code.
oh, yeah, this is going to be working problems out on paper. Yeah. Okay. All right. So sometime next week, I'll have a practice test ready. Okay. I sense people are really done now. Well, okay. I am too.